Hello and welcome to Engineers Mindset Academy. Alright, so it's been a whole lot of series going through Laplace transformation, and finally we are on solution of differential equations with Laplace transformation. Now we have a question on the board. Now, before solving this question, I'm going to be showing you some key shortcuts and points which you need to know before utilizing Laplace transformation to solve any problem on differential equation. So sit tight while we begin the class. Welcome back. Alright, there are 4 key steps which you need to know to be able to solve differential equation problems using Laplace transformation. But before going into those steps, let's consider, first of all, let's say S. Let S be a function of t at t is equal to 0 and x equals x naught. So this is the given condition. Of course, you know, whenever a problem is given to you in differential equation, you must always be given initial condition. So this is the initial condition. T is equal to 0 and x is equal to what? X naught. Now we are simply saying that x is a function of t. So if x is a function of t, it means I can only differentiate x with respect to t. Therefore, the first thing you need to consider is this, that the x all over the t is equal to x1. Keep this in mind. Okay, next is the squared x all over the t squared. Call this what? X2. Next is the 3x all over the t3 is equal to x3. Next is the 4x all over the t4 is equal to what? X4. So and so on. Finally, if you have the nx all over the tn, it is simply what? Xn. So keep this in mind. This is the first shortcut I want you to know always, that the x dt is simply what? Called x1. The squared x over the t squared is called x2. The cube x over the t cube is called x3, and so on. Now that's the first thing to note. The second thing to note is the Laplace transformation of x. The Laplace transformation of x is simply taken as what? X bar. Alright, so the Laplace transformation of x is simply called x bar. Next, the Laplace transformation of the x all over the t is simply taken as x times x bar minus x naught. Remember, x naught is what? Obtained from initial condition. When t is equal to 0, x is equal to x naught. Okay, so the Laplace transformation of the x over the t is taken as x times x bar minus x naught. Always know this. Next thing you need to know is the Laplace transformation of the squared x all over the t squared. So if you're given a differential equation of second order, then this is equal to, again, remember, since this is second order, then this becomes x all squared multiplied by x bar minus, then you append x here, it becomes x times x naught, now minus x1. Always keep this in mind. Okay, again, if the order is third order differential equation, then you have that the Laplace transformation of the 3x all over the t3 is simply equal to, now you also build from this. Remember, if it is order 3, then x becomes what? X to the power of 3 multiplied by x bar. Next becomes, now x becomes x squared multiplied by x naught. So I have x squared multiplied by x naught. So you continue from there. After x naught, next is x1, but then I have to exhaust all the values of what? X. So which means I'm going to be having times x now reduced to what? X. Alright, x squared now reduced to what? X. Alright, so multiply by s1, then x is completely exhausted, remaining what? X naught. So you simply call this what? X2. So in this case, I have an invisible x naught there, and x to the power of 0 remains what? 1. So I'm left with what? X2. Again, if it is of fourth order, let's say Laplace transformation of the fourth x all over the t fourth. Similarly, it's still the same. Then you start with what? X to the power of 4 multiplied by what? X bar from here minus, now it reduces. This becomes now x to the power of 3 multiplied by what? X naught. See from here. Now we are done with x naught. Then we'll start building from here. X1, x2, and so on. Okay. Next becomes s now reduces to what? X squared times x1 minus this becomes what? X1 times x2. Okay, so just x now becomes x to the power of 1 times x2. That means the next becomes now x now to the power of 0, which remains 1, times this becomes x3. So you keep this is how you differentiate. Now keep all of this in mind. Okay, we are going to be using all of this towards solving that problem. So if you're asked to solve a differential equation, first the Laplace of x automatically is x bar. If it is differential equation of order 1, just like we have here, then the Laplace of the x all over dt is simply x times x bar minus x naught. Okay, where x naught is obtained from where the initial condition. Same thing as x1. x1 is also obtained from the initial condition. Same thing here as x2 and x3. So if it is differential equation of order 2, then you have the Laplace of the squared x over the t squared to be equal to what? X squared multiplies x bar minus x naught minus x1, and so on. Now, keeping this in mind, there are 4 steps. There are 4 steps to solving any differential equation problem using Laplace transformation. The very first step is write the Laplace transformation of all the functions involved in the differential equation. That is step 1. Step 2, insert the initial conditions given. Insert the initial conditions given. That's step 2. Step 3, rearrange the equation to obtain the Laplace transformation of the solution. Rearrange the equation to obtain the Laplace transformation of the solution. And the final step is find the Laplace inverse of the given solution. Find the Laplace inverse of the given solution. That gives you the solution of the differential equation. So 4 key steps. Let's start. Now we are given a question on the board. The x over the t plus 2x is equal to 10 exponential 3t. Now this is differential equation of order 1 because I'm saying what just the x all over the t. So this is order 1 differential equation. Remember the first step. Write the Laplace transformation of each of the functions involved in where the differential equation. So which means in this equation I have Laplace of the x all over the t plus Laplace of 2x, okay, and this is equal to Laplace of 10 exponential 3t. All right, so that is the first step. Write the Laplace transformation of all the functions involved. All right, so I'm going to be pulling out 2 and 10 since they are constant. Pull them out of the Laplace transformation symbol. So this becomes Laplace of the x all over the t, all right, plus pulling 2 out, now I have 2 Laplace of x, okay, and this is equal to pulling 10 out here, I have 10 Laplace of exponential 3t. All right, so we have this. Now, not forgetting Laplace transformation of the x all over the t. We said it earlier that this is equal to what? X times x bar minus x naught. It's as simple as this. Next, I have the Laplace transformation of x. We said it earlier, Laplace transformation of x simply is equal to what? X bar. You have this. The next thing to find out is the Laplace transformation of 10 the Laplace transformation of exponential 3t. Alright, so in the table of standard values, which I explained in the very first 3 videos, or in the very first video I did on Laplace transformation, contains the explanation to this. Now, in that video I said the Laplace transformation of an exponential function is always given as 1 all over s minus the number attached to the exponential function. So this is what? 3. The number there is plus 3. So since this is plus 3, then it becomes 1 over x minus 3. But if the number attached to the exponential sign is minus 3, automatically it becomes 1 all over x plus 3. Hence, the Laplace of exponential 3t is simply equal to 1 all over x minus 3. Having this already, you can plug this now back into the equation. So let's call this equation 1. Plugging all of this back into the equation, the Laplace of the x all over the t, we know the value to be this. So we simply have x times x bar minus x naught, okay, plus 2 times the Laplace of x, and Laplace of x gives us what? X bar. So we have times x bar, okay, and this is equal to 10 times the Laplace of what? Exponential 3t. And Laplace of exponential 3t gave us 1 over x minus 3. So we have 10 times 1 all over x minus 3. You have something like this. Okay, so you can rewrite this to be what? X times x bar minus x naught, okay, plus 2 x bar, and this is equal to, so 10 times 1 will give us 10 all over x minus 3. This is the first condition obeyed. Write the Laplace transformation of each of the given function. The second condition says insert the initial conditions given. From the question we are given that at t is equal to 0, x is equal to 6. Now that condition says at t is equal to 0, x. This x now is simply what? X naught. Remember what I said earlier? At t equal to 0, x equals x naught. So x equals x naught and the value is equal to 6. So they are simply telling us that x naught is equal to 6. So the second condition says insert the initial condition into the equation obtained. And this is what we have obtained so far. So we need to now insert what? X naught to be equal to what? 6 in the initial condition, which is the initial condition. So in this equation now, I have x bar minus, I'm having there, or I'm seeing x naught there, and x naught is simply equal to what? 6. So you simply append 6 there. So it becomes x bar minus 6, okay, plus 2x bar, and this is equal to 10 all over x minus 3. You simply have this. Now, this is the second law obeyed. The third law says rearrange the equation to find or to obtain the Laplace transformation of the given solution. Now, what's the Laplace transformation of the given solution? Simply s bar and s bar. So we have to rearrange this equation in terms of what? S bar. So we simply rearrange. Collecting like terms now, I have s bar, let's bring them closer, plus 2s bar minus 6 is equal to 10 all over s minus 3. I have something like this. Okay, now x bar is common between these two, so you can factor s bar. So I have x bar all into, this becomes s plus 2, okay, minus 6, and this is equal to 10 all over s minus 3. Remember, rearrange to find the solution, the Laplace transformation of the solution. So we need to make x bar, this is the Laplace transformation of the solution. We need to make x bar subject. Therefore, let's send minus 6 over to this side of the equation. Hence, we have that x bar into s plus 2 is now equal to 10 all over x minus 3. If minus 6 cross an equal to sign, it becomes plus 6. So I have something like this. Alright, I can still continue solving here. Okay, so I have here x bar into x plus 2 is now equal to 10 over x minus 3 plus 6. Now I need to make x bar subject, which means I have to divide both sides by what? X plus 2. Hence, this now implies that x bar is equal to, this is 10 all over x minus 3. If I divide that value by x plus 2, I will have into s plus 2 plus, same thing here, this becomes 6 all over s plus 2. So we simply have this. This is the third condition obeyed. First condition, write the Laplace transformation of all the functions involved in the differential equation. Next condition, insert the initial condition. After that, the third condition says rearrange the equation to obtain the Laplace transformation of the solution, which is what we've done now. We've obtained the Laplace transformation of the solution. The final catch says take the Laplace inverse of this function. It gives you the solution of the differential equation. So we simply what? Take Laplace inverse of x bar. So this is actually the Laplace inverse of each of these functions involved here. 10 all over x minus 3 into x plus 2. Okay, plus the Laplace inverse of 6 all over s plus 2. Alright, so this is what it is. So the Laplace inverse of x bar is simply the Laplace inverse of everything, or the result of x bar, which we'll have there. Okay. Alright, so if you watch earlier, I said I said that let x be equal to what? F of t. Then the Laplace transformation of x will give us what? X bar. So this simply means that the inverse transform of x bar will simply give us what? x, that's obtaining back the given function. So the Laplace inverse of x will simply give us x. All right. But then notice that I have Laplace inverse of 10 over x minus 3 times x plus 2. And then Laplace inverse of 6 all over x plus 2. Let's pick them out individually to solve. So call this equation 2. Let's pick them out individually. I will consider the simpler one now. Laplace inverse of 6 all over x plus 2. This is simple. I can simply write this, since 6 is a constant, pull 6 out. I will have 6 times the Laplace inverse of 1 all over s plus 2. Now, from the table of standard values, which we discussed earlier from beginning of the video on Laplace transformation, I said that the Laplace transformation of an exponential function, let's say exponential at, is simply given as what? 1 all over x minus a, where a is a number attached to the what? Exponential function. So this simply means that the Laplace inverse of 1 over s minus a, automatically I should know, will give me what? Exponential at. But observe that the number here is what? Positive. And since it's positive, I'm having 1 over x minus a. So that means that the Laplace transformation of exponential minus at, now when the number attached to the exponential sign becomes negative, this is going to now be what? 1 all over s minus, now a becomes minus a. It becomes minus a. And this is simply equal to 1 all over s minus times minus becomes plus. So I have 1 over s plus a. So hence, whenever I notice a positive sign at the denominator, it simply means that the value of a was what? Negative in the exponential function. Now, I am seeing Laplace inverse of 1 over s plus 2. Mind you, 2 now becomes what? This a. And since this is plus, that means the Laplace inverse of 1 all over s plus 2 is simply what? Exponential. Now, this is plus 2 and this is plus 2, and this is plus a, but plus a came when we have exponential minus at. Hence, this is actually what? Exponential minus 2 times t. Therefore, the Laplace inverse of 1 over h plus 2 is simply exponential minus 2 times t. All right. Right, so this is now equal to 6 times. Now, the Laplace inverse of 1 over x plus 2, we have obtained it to be what? Exponential minus 2t. So this part is solved. We know this part. Then we need to find the Laplace inverse of this part. Laplace inverse of 10 all over x minus 3 times s plus 2. Now, this is a compound fraction, and we've already done this in the previous video, Laplace transformation involving partial fractions or compound fractions. In this case, since we have a compound fraction, it will be difficult for us to what? Be able to find a Laplace inverse of this function. So the only thing to do is to what? Resolve this compound fraction into two simple fractions, simply called the partial fractions. All right, and to do that, you simply what? Consider, okay, that 10 all over x minus 3 times s minus 2, and this is equivalent, breaking this now into two simple fractions. We have a all over x minus 3, okay, plus b all over s plus 2. All right, so you have something like this, okay. Hence, 10 over s minus 3 times s plus 2 is now equivalent. You obtain the what? LCM of the right hand side. So the LCM is still what? The multiple of denominators. So you still have s minus 3 times s plus 2 as the LCM. Now, this LCM divides x minus 3. X minus 3 cancels x minus 3. So I'm left with s plus 2. S plus 2 multiplies a, simply gives us a times s plus 2. Okay, plus b into the LCM once more divides s plus 2, denominator of b, and s plus 2 cancels s plus 2. So I'm left with x minus 3. X minus 3 times b itself becomes b times s minus 3. So I have something like this. Now, from the theorem or principle of partial fractions, if the denominators are equal, then automatically the numerators must be equal. Since denominators are equivalent, therefore their numerators must also be what? Equivalent. So this simply implies that the numerators will be equivalent. So I'm going to be equating their numerators now. Hence, I will have 10 is equivalent to A into S plus 2, okay, plus B into S minus 3. So I have this. In order to find A, then you look into the bracket of B, pick the inverse of the number in that bracket and put it in place of X. That will nullify the effect of B and help us to find the value of A. Now, what do I mean? I want to find A, then look into the bracket of B. In B, I have X minus 3. Minus 3 is the number there. Hence, if I place S to be what's the opposite of minus 3, opposite of minus 3 is simply plus 3. So if I set S to be plus 3, then wherever you see S, put in the value as plus 3. That will help to what? Nullify the effect of B and help me find A. So to find A, you've set S. To find A, okay, set S to be equal to 3. Therefore, this is 10 equivalent to A. Wherever you see S now, put in the value as 3. I have X plus 2 here. In place of X, it becomes 3 plus 2, okay, plus B into, I have X minus 3, and X now is what? 3. So it becomes 3 minus 3. So you notice now that 3 minus 3 is 0. Therefore, B automatically becomes cancelled out. Okay. All right, so I'm going to be continuing from here, still keeping my equation 2 because I will need this particular equation. So I'll continue from here. All right, so from here now, this shows that 10 is equivalent to, let's expand the bracket now. 3 plus 2 is 5. 5 times A gives us 5A. And of course, 3 minus 3 is 0. 0 times B becomes 0. That one is off. Therefore, I can find A. A becomes what? 10 divided by 5. This simply implies that my A is actually equal to 2. Same thing, to find B, I will still do that over here. Now, you want to find B, you look into the bracket of A, look for the value in that bracket, take the opposite of that value and put in place of X. That will nullify the effect of A in that particular bracket and help us to find B. So this is bracket of A. I have X plus 2. So the number in that bracket is what? Plus 2. The opposite of plus 2 becomes what? Minus 2. So I will simply say let S be equal to minus 2 in that equation. That will help nullify the effect of A and help me to find B. All right. So to find B now, to find B, simply set S to be equal to what? Minus 2. I will set S to be minus 2. Therefore, I have 10 is now equivalent to A into, this is S plus 2, and S now is minus 2 plus 2, okay, plus B into, I have X minus 3. S now is minus 2, so it becomes minus 2 minus 3. Okay, now, mind you, minus 2 plus 2 is 0, so this cancels the effect of A. Hence, I have that 10 is equivalent to, of course, A is cancelled. Then I have minus 2 minus 3, which is minus 5 times B. That gives us minus 5B. So this simply implies that B itself is equal to 10 all over minus 5. And therefore, B is actually what? Minus 2. All right. So having found the value of A and the value of B, we can now what? Substitute into this equation for A and B. That means this compound fraction having broken down into what? Two simple fractions, then we can now use the Laplace inverse to solve the problem. Okay, we can do it over here. All right, so this means now, this implies that the compound fraction 10 all over S minus 3 times S plus 2, which we obtained here, is now equivalent, we did it here, is equivalent to A all over X minus 3. What is A? A is given as what? What? 2. So in place of A, we put in 2 all over S minus 3, okay, plus B, but B is minus 2. It becomes minus 2 all over S plus 2. Okay, so it means that we have been able to now transpose this compound fraction into two simple fractions. Then we can rewrite the Laplace inverse of the compound fraction. Okay, so I can take care of now, since I already have this. Okay, all right, so this Laplace inverse is now equal to what? The Laplace inverse of the individual partial fractions which we just obtained. So this is now equal to Laplace inverse of 2 all over s minus 3, okay, plus the Laplace inverse of something, but this is now minus 2 all over s plus 2. You have this. So the Laplace inverse of this compound fraction simply becomes the Laplace inverse of their individual partial fraction or individual simple fractions. You have this. All right, so we can now write this. I think I can take this off, or let's take here off. Again, I can now pull out 2, okay, pull out 2, so it becomes just 1 there. This now becomes 2 times Laplace inverse of 1 all over s minus 3, okay. Also, pull out minus 2 there, it becomes minus 2 times Laplace inverse of 1 all over x plus 2, s plus 2. So you simply have this. Now, once again, I explained in the introduction video or when we talked about table of standard values that the Laplace transformation of an exponential function raised to the power of at is simply equal to what? 1 all over s minus a. It's simple as this. Now, this simply implies that the Laplace inverse of 1 over s minus a should automatically give me back my what function, which is equal to exponential at. Now, keeping this in mind, I'm seeing Laplace inverse of 1 over x minus 3. Not forgetting that 3 is a number as a. A here stands for that number, and we have it here to be 3. So, comparing the two, it simply means that Laplace inverse of 1 over x minus 3 automatically becomes what? Exponential. Therefore, the Laplace inverse of 1 all over s minus 3 automatically becomes exponential 3t because 3 becomes the number. It's as simple as this. So this is actually exponential 3t. Similarly, I have here to be 1 over x plus 2, and I said when the exponential function is raised to a positive number, you have here to be what? Negative x minus a. But if the exponential function is raised to a negative number, that means here is going to be what? Positive. So which simply means that since I have x plus 2, then the Laplace inverse of 1 over x plus 2 becomes what? Exponential minus 2. In that case, the exponential function is raised to what? A negative value. All right, so please do well to watch the table of standard values from the very first video. I did about 3 videos on table of standard value. So do well to watch the 3 of them for proper understanding. But let's effect all of this now. All right, so this now implies this is now equal to 2 times 1 over x minus 3 becomes 2. Laplace inverse of 1 over x minus 3 is simply exponential 3t, okay? Minus same thing here, 2. Laplace inverse of 1 all over x plus 2, since it's plus now, it becomes exponential minus 2t. All right, so you simply have this. So this is now the Laplace inverse of what? This compound fraction. Hence, we'll find the Laplace inverse of this, which gave us 6 exponential minus 2t, and now we'll find the Laplace inverse of this. Therefore, the solution of the differential equation can now be written as, let's take here off. Okay, let's take here off. All right, so the solution of the differential equation now can now be written as, remember, Laplace inverse of x bar will simply give us what? X, and this is equal to the Laplace inverse of this compound fraction. We have found it to be what? This 2 exponential 3t minus 2 exponential minus 2t, then plus Laplace inverse of 6 all over x plus 2, which we obtain here as 6. So plus 6 exponential minus 3 minus 2t. Okay, so this becomes the solution to that differential equation. All right, guys, so that is how you solve differential equation using Laplace transformation. Once more, don't forget, always consider the Laplace of x to be what? X bar. If the solution is first order differential equation, then you have Laplace of the x all over the t to be what? X times x bar minus x naught. If it is second order, then Laplace of the squared x over the x squared becomes x squared times x bar minus x naught minus x1, and it continues like that. All right, I will see you in the next video with more questions on differential equation solution using Laplace transformation. Thanks and cheers.